Welcome to Wildlife for Sleep. This channel is a quiet place where wildlife and ancient worlds come together to help you relax, unwind, and drift into deep rest. If you enjoy my work like this and find them helpful for sleep or relaxation, please like the video, subscribe to the channel, and share your thoughts in the comments. Your support helps this channel grow and allows me to create more peaceful content for you. Now, get comfortable and let the journey begin. Megalodon existed within a long continuum of shark evolution that began hundreds of millions of years before its appearance. Sharks first evolved during the Silurian period, more than 420 million years ago. These early forms were among the first vertebrates to develop jaws, a feature that allowed more efficient feeding and supported diversification into many ecological roles from the beginning. Sharks were characterized by skeletons made of cartilage rather than bone, multiple rows of replaceable teeth, and sensory systems adapted specifically for life in water. Throughout the Paleozoic and Mesozoic eras, sharks persisted through several mass extinction events, while many marine groups disappeared entirely. Shark lineages survived with relatively minor structural changes. Their success was due to adaptability, efficient body design, and reproductive strategies that favored resilience over specialization. By the time dinosaurs dominated terrestrial ecosystems, sharks were already well established in marine environments across the globe. Megalodon belonged to a group of sharks known as lamniforms, an order that includes several large predatory species alive today. Lamniform sharks share a general body plan that includes a torpedo-shaped body, a strong caudal fin, large pectoral fins, and a mouth adapted for capturing sizable prey. Within this order, a lineage referred to as megatooth sharks gradually evolved larger body sizes and more robust teeth. The megatooth lineage can be traced through fossil teeth attributed to species such as Otodus obliquus, Otodus axuaticus, and Otodus tubutensis. These species lived between approximately 60 and 28 million years ago. Over this time span, the teeth show gradual increases in size, thickness, and the development of serrated edges. These changes indicate a shift toward feeding on larger prey and processing tougher tissue, including bone. Megalodon, scientifically classified as Otodus megalodon, appeared during the early Miocene epoch around 23 million years ago. Its emergence coincided with major changes in marine ecosystems. Following the extinction of large marine reptiles at the end of the Cretaceous period, marine mammals began to diversify. Early whales evolved rapidly, increasing both in number and body size. This created a new and abundant food source for large marine predators. The Miocene world differed significantly from the modern Earth. Global temperatures were higher, and permanent ice caps had not yet formed at the poles. Sea levels were elevated, flooding continental margins and creating extensive shallow seas. These environments supported high biological productivity, particularly along coastlines where nutrient input from land combined with sunlight to fuel plankton growth. Megalodon evolved within this context of warm oceans and abundant prey. Its increasing size was not sudden, but occurred gradually over many generations. Individuals that could exploit large marine mammals gained access to high-energy food sources, supporting further growth and reproduction. Over time, natural selection favored traits associated with size, strength, and long-distance movement. Early megalodons were likely smaller than the largest individuals known from later in the Miocene. Fossil evidence suggests that juveniles occupied shallow coastal environments that functioned as nursery areas. These regions provided protection from open ocean competition and access to smaller prey suitable for growing sharks. As individuals matured, they moved into deeper and more open waters. Megalodon did not emerge as an isolated anomaly. It represented the culmination of a long evolutionary trend within predatory sharks toward increased size and specialization for hunting large vertebrates. Its existence was closely tied to the structure of Miocene marine ecosystems and the availability of suitable prey. At this stage in its history, Megalodon was a successful and expanding species, well adapted to the conditions of its time. Its full dominance of the marine environment would develop gradually as its anatomy, behavior, and ecological role continued to evolve. Miocene oceans and global distribution. During the Miocene epoch, the structure of the world's oceans supported large marine predators more effectively than at almost any other time in Earth's history. Global temperatures were higher than today, and the absence of permanent polar ice allowed warm water to circulate freely between equatorial and higher latitudes. This created broad temperature gradients rather than sharp thermal boundaries, expanding the range of species adapted to warm and temperate waters. Sea levels were significantly elevated. Large portions of present-day coastal regions were submerged beneath shallow seas. These continental shelf environments were among the most productive marine habitats, receiving sunlight, nutrients, and steady water circulation. Plankton populations flourished, forming the base of a complex food web that extended upward to large fish and marine mammals. Ocean circulation patterns during the Miocene differed from those of the modern world. The closure of certain seaways had not yet occurred, and others were still forming. The Central American Seaway, for example, remained open, allowing water to flow freely between the Atlantic and Pacific Oceans. This exchange equalized temperatures and distributed nutrients widely, contributing to stable marine productivity. Within this global ocean system, Megalodon achieved a wide geographic distribution. Fossil teeth attributed to the species have been found on every continent except Antarctica. These discoveries indicate that Megalodon occupied coastal and offshore waters across the Atlantic, Pacific, and Indian Oceans. Its range extended through tropical regions and into temperate zones, following favorable water temperatures and prey availability. Megalodon was not restricted to a single habitat type. It inhabited open ocean environments, continental shelf regions, and areas near coastlines. However, evidence suggests a degree of habitat differentiation by age. Juvenile individuals were more commonly associated with shallow coastal waters, where predation risk was lower and smaller prey were abundant. Adults, by contrast, ranged widely across open seas, where large marine mammals were more common. Migration likely played a role in Megalodon's life history. Seasonal changes in water temperature and prey distribution would have influenced movement patterns. Whales migrated between feeding and breeding grounds, and Megalodon likely followed these routes. Its large body and efficient swimming mechanics made long-distance travel energetically feasible. The distribution of Megalodon fossils also reflects long-term environmental stability during much of the Miocene. For several million years, ocean conditions remained relatively consistent, allowing large predators to maintain extensive ranges. This stability reduced pressure for rapid adaptation and supported long-lived species with slow growth rates. Regional differences did exist. In some areas, upwelling zones brought nutrient-rich deep water to the surface, increasing productivity and attracting dense concentrations of prey. These zones would have been particularly important feeding areas for large sharks. In contrast, less productive regions may have served primarily as transit corridors rather than permanent habitats. Despite its size, Megalodon did not dominate every marine environment equally. Its presence depended on sufficient prey density and suitable water temperatures. Cooler waters likely limited its range, particularly as global climates began to cool toward the late Miocene and Pliocene. Even so, during its peak, Megalodon was among the most widely distributed large predators in the oceans. The Miocene ocean provided the space, warmth, and biological productivity necessary for Megalodon to thrive. Its global distribution reflected both its physical capabilities and the interconnected nature of ancient seas. This widespread presence set the stage for its role as a major regulator of marine ecosystems, influencing prey populations and shaping evolutionary pressures on other species. With the environmental context established, the focus now shifts to how Megalodon functioned within this system on a daily basis, including movement patterns, feeding behavior, and energy use. Megalodon's daily life was shaped by the need to balance energy intake with energy expenditure. As a very large predator, it did not need to feed frequently, but successful feeding events had to provide substantial nutritional return. This requirement influenced how the animal moved, where it spent time, and how it interacted with its environment. Most evidence suggests that Megalodon spent much of its time in steady, continuous motion. Like many large sharks, it likely relied on forward movement to ventilate its gills efficiently. This did not require fast swimming, Instead, Megalodon probably cruised at moderate speeds, conserving energy while covering long distances. Such movement allowed it to patrol large areas of ocean, increasing the chance of encountering prey or detecting signs of injured animals. The vertical range of Megalodon was likely limited compared to deep-diving marine mammals. It primarily occupied the upper layers of the ocean, including surface and mid-water zones where large prey were most abundant. While it may have occasionally descended to greater depths, particularly when following prey, its physiology was best suited to waters where temperature and pressure remained within moderate ranges. Feeding behavior in Megalodon was based on efficiency rather than prolonged pursuit. Its preferred prey included medium to large marine mammals, particularly whales. Fossil evidence from whale bones bearing large bite marks consistent with Megalodon teeth supports this interpretation. These marks are often found on flippers, tail vertebrae, and rib cages, indicating targeted attacks aimed at disabling the animal quickly. Rather than attempting to kill prey through suffocation or exhaustion, Megalodon likely focused on inflicting catastrophic injury. A powerful bite to a whale's flippers or tail would severely impair movement, reducing the prey's ability to escape. Once mobility was compromised, further bites could be delivered with reduced risk and lower energy cost. Megalodon's wide jaws and large teeth allowed it to remove large sections of flesh in a single bite. This feeding strategy minimized the time spent interacting with prey, reducing exposure to injury. After feeding, Megalodon may have withdrawn and allowed the prey to weaken or die before returning to consume additional tissue. Scavenging likely supplemented active hunting. Large marine animals that died from illness, injury, or other causes would have provided significant food resources. The ability to detect chemical cues in the water would have allowed Megalodon to locate carcasses from considerable distances. Scavenging reduced energy expenditure and risk, while still supporting the nutritional demands of a large body. Feeding events were probably followed by extended periods of reduced activity. Digesting large amounts of protein and fat requires time. And Megalodon's metabolism, while higher than that of smaller sharks, was still adapted for efficiency rather than constant feeding. During these periods, the shark may have remained in warmer waters that facilitated digestion. Interactions with other large predators were likely limited. Megalodon occupied the top trophic level in its environment, and few animals posed a threat to a fully grown individual. However, competition for food would have existed with other large sharks and early predatory whales. Such competition may have influenced feeding locations and timing, rather than leading to direct confrontation. Juvenile megalodons had different daily patterns. Smaller body size required more frequent feeding, and their prey consisted mainly of fish, smaller sharks, and young marine mammals. Nursery habitats provided both food and relative safety, allowing juveniles to grow steadily before transitioning to open ocean lifestyles. Daily activity was not uniform across all regions. In areas with high prey density, Megalodon may have remained within limited ranges for extended periods. In less productive areas, it likely traveled more extensively. These flexible patterns allowed the species to exploit a wide range of environments without overexploiting any single area. Overall, Megalodon's daily life was defined by movement, sensory monitoring of the environment, and infrequent but highly effective feeding. Its behavior reflected a balance between the demands of size and the opportunities provided by a productive Miocene ocean. By the time Megalodon reached full adulthood, its growth had slowed, body proportions stabilized, and energy was no longer directed primarily toward increasing size, but toward maintaining a massive and complex organism within a dynamic marine environment. At this stage, adult individuals occupied the highest trophic level of the Miocene oceans, with no consistent natural predators and few direct competitors capable of challenging them. Adult megalodons ranged widely across open seas, their movements influenced by water temperature, prey availability, and seasonal changes in ocean productivity. They were not territorial in the strict sense, but repeated use of productive regions likely occurred, especially in areas where large marine mammals congregated. Migration routes of whales provided predictable opportunities for feeding, and adults likely timed their movements to coincide with these patterns. Energy management was central to adult life. A single successful feeding event on a large whale could provide sufficient calories for extended periods. After feeding, activity levels likely decreased as digestion proceeded. During these intervals, Megalodon may have remained within warmer water masses that supported metabolic efficiency and reduced energy loss. Despite their dominance, adult megalodons existed within a broader predator community. Other large sharks, including species such as large lamniforms and early members of the lineage that would later give rise to modern killer whales, shared portions of the marine environment. Competition occurred indirectly through prey use rather than through frequent physical confrontation. Differences in hunting strategy, prey size preference, and habitat use reduced direct overlap. Megalodon's presence exerted strong influence on marine ecosystems. Large marine mammals evolved behaviors that may have reduced predation risk, including changes in migration timing, group formation, and habitat preference. Fossil evidence suggests that some whale species developed more robust skeletal structures during the Miocene, possibly as a response to increased predation pressure from large sharks. Population density of adult megalodons was likely low. Large body size, slow growth, and limited reproductive output would have constrained population numbers. This low density reduced intraspecific competition and helped maintain ecological balance. Individual adults may have occupied expansive ranges without frequent encounters with others of their species outside of mating periods. As adults aged, physical wear accumulated gradually. Teeth were continuously replaced, but other aspects of the body, such as cartilage and muscle, likely experienced slow degradation over time. Aging individuals may have become less efficient hunters, relying more heavily on scavenging or smaller prey. Even so, their size alone would have provided continued access to food with relatively low risk. For millions of years, this system remained stable. Warm oceans supported large prey populations, migration routes persisted, and Megalodon continued to reproduce, grow, and age within an environment well suited to its needs. The species did not expand endlessly, nor did it decline rapidly. It existed in long-term equilibrium with its surroundings. This stability, however, depended on environmental conditions that were not permanent. Subtle changes in global climate were already underway, altering ocean temperatures and circulation patterns. These changes would gradually affect prey distribution, reproductive success, and habitat availability. For the moment, during its peak, Megalodon remained an established component of the marine world, sustained by abundance, supported by warmth, and shaped by slow biological processes that unfolded across deep time. Toward the later Miocene, conditions that had supported large marine predators for millions of years began to shift, not abruptly, but gradually, through changes in climate, ocean circulation, and habitat structure that accumulated over long spans of time. These changes did not target Megalodon directly. They altered the system on which it depended. Global temperatures began to decline slowly. The first permanent ice sheets started to form at higher latitudes, and the difference between warm equatorial waters and cooler polar regions increased. This growing temperature gradient strengthened ocean currents and altered their paths. Some regions became more productive, while others experienced reduced nutrient availability. Sea levels responded to cooling climates, falling gradually as ice accumulated on land. Shallow seas that had once extended far inland began to recede. Coastal shelf habitats shrank, reducing the availability of warm, protected nursery areas that had supported juvenile megalodons. These environments did not disappear entirely, but they became more fragmented and less stable. Changes in ocean circulation also affected prey species. Whale populations continued to evolve, but their distribution shifted. Some species adapted to cooler waters, others altered migration routes, and some declined. As prey became less predictable in location and timing, large predators that relied on consistent access to high-energy food faced increasing challenges. At the same time, new competitors emerged. Early members of the lineage leading to modern killer whales began to diversify. These animals hunted cooperatively, targeted similar prey, and were more flexible in diet and habitat use. Unlike Megalodon, They could exploit a wider range of prey sizes and adapt more quickly to environmental change. Competition was not necessarily direct, but overlap increased. In regions where large marine mammals became less abundant, the presence of multiple apex predators increased pressure on shared food resources. Megalodon size, once a clear advantage, now carried greater energetic cost. Cooling oceans also placed physiological demands on large sharks. Maintaining body temperature became more challenging as warm waters contracted toward the equator. While Megalodon likely possessed some degree of regional endothermy, allowing partial internal temperature regulation, this adaptation had limits. Reduced access to warm habitats increased metabolic stress. Reproductive success may have declined during this period. Fewer stable nursery areas, combined with changing coastal conditions, likely reduced juvenile survival rates. Because Megalodon reproduced slowly and produced relatively few offspring, even small decreases in recruitment could have significant long-term effects on population stability. These pressures accumulated quietly. There was no single event that marked the beginning of decline. Instead, survival became less certain with each passing generation. Individuals still reached adulthood, still fed successfully, but population resilience weakened. The marine ecosystem itself continued to reorganize. Smaller, more adaptable predators increased in relative importance. Food webs shortened in some regions while becoming more complex in others. Megalodon remained present, but its dominance was no longer absolute. For a time, the species persisted alongside these changes. Evolution does not operate on awareness, only on outcomes. Traits that had once ensured success now limited flexibility. Large size required stable conditions, abundant prey, and warm seas. As those conditions continued to erode, Megalodon's future narrowed slowly, without sudden collapse, without clear boundaries, only gradual constraint. By the transition from the late Miocene into the early Pliocene, the environmental pressures affecting Megalodon had become more pronounced. Global cooling continued. Ice sheets expanded further at the poles, and seasonal variation in ocean temperature increased. Warm water zones narrowed, especially at higher latitudes, limiting the range of habitats suitable for a very large, warm, adapted shark. Sea levels continued to fluctuate, altering coastlines and reducing the extent of shallow continental shelf environments. These regions had played an important role in Megalodon's life cycle, particularly as nursery habitats for juveniles. As such areas became less widespread and more fragmented, the survival rate of young individuals likely declined further. At the same time, marine mammal communities were changing. Some whale species increased in size and speed, others shifted toward colder waters, and many developed new migration patterns. These changes reduced the predictability of prey availability. For a predator dependent on large, energy-rich animals, unpredictability increased the cost of survival. Competition intensified. Early forms of modern odontocetes, including ancestors of killer whales, expanded their ecological roles. These predators hunted in groups, coordinated their behavior, and exploited a broader range of prey sizes. Their social structure allowed them to adapt quickly to changing conditions, something Megalodon could not do. Fossil evidence suggests that Megalodon populations declined unevenly across regions. In some areas, the species disappeared earlier, while in others it persisted longer. This pattern is consistent with gradual environmental change rather than a sudden extinction event. Regions that retained warmer waters and higher productivity supported Megalodon populations for extended periods. Eventually, however, the cumulative effects became too great. Reduced reproductive success, increased energetic demands, shrinking habitat range, and competition for prey combined to limit population recovery. Once numbers fell below a sustainable threshold, extinction became inevitable. The last known Megalodon fossils date to approximately 3.6 million years ago. After this point, no confirmed evidence of the species appears in the geological record. The megatooth shark lineage, which had persisted for tens of millions of years, came to an end. The extinction of Megalodon did not cause a collapse of marine ecosystems. Instead, ecological roles shifted. Other predators expanded into niches previously occupied by large sharks. Marine mammal populations adjusted over time, and food webs reorganized in response to new balances of predation and competition. Megalodon left behind no skeletons, no direct physical remains beyond teeth and scattered vertebral fragments. Teeth remain the primary source of information about its size, distribution, and behavior. These fossils are found embedded in ancient seabeds, river sediments, and uplifted marine deposits now exposed on land. Scientific understanding of Megalodon continues to develop. Advances in biomechanics, isotope analysis, and comparative anatomy have refined estimates of size, bite force, growth rates, and ecological role. Each discovery adds detail, but the overall picture remains consistent. Megalodon was a highly specialized apex predator, well adapted to a specific set of environmental conditions that did not persist indefinitely. The disappearance of Megalodon illustrates a broader pattern in Earth's history. Even the most successful and dominant species remain dependent on environmental stability. When conditions change beyond the limits of adaptation, extinction follows, not as a failure, but as a natural outcome of biological constraint. With its extinction, Megalodon passed fully into deep time. Its influence remains visible in the fossil record, in the evolutionary history of marine mammals, and in the structure of modern ocean ecosystems shaped by what came before. Knowledge of Megalodon comes almost entirely from fossil remains, primarily teeth, with occasional vertebral fragments and rare jaw elements preserved under specific conditions. Unlike bony fish or marine mammals, Sharks possess skeletons made of cartilage, a material that decays quickly after death and is unlikely to fossilize. As a result, teeth provide the most consistent and informative record of Megalodon's existence. Megalodon teeth are among the largest shark teeth ever discovered. Their size, thickness, and serrated edges distinguish them clearly from those of other species. These teeth have been found in marine sediment layers dating from the Miocene to the early Pliocene, often in association with fossilized whale bones and other marine mammals. The global distribution of these teeth confirms the species' wide geographic range, and an individual megalodon would have shed thousands of teeth over several decades. This constant replacement explains why teeth are relatively common compared to other remains. Each tooth carries information about feeding behavior, jaw structure, and overall body size. Measurements of tooth height and width allow scientists to estimate total length using scaling relationships derived from modern sharks. Vertebral centra, when preserved, provide additional insight. Growth rings within these structures indicate age at death and growth rates. Analysis of these rings suggests that Megalodon grew rapidly during early life and more slowly as it approached adulthood, a pattern consistent with large modern sharks. These data support estimates of long lifespan and delayed maturity. Bite marks on fossil whale bones provide direct evidence of feeding behavior. Many bones show large, semicircular gouges that match the shape and spacing of Megalodon teeth. Some marks indicate repeated biting, while others suggest targeted strikes to flippers or tails. These patterns align with biomechanical models of efficient prey immobilization. Scientific reconstruction of Megalodon relies on comparison with living lamniform sharks. The great white shark serves as a particularly useful analog due to similarities in tooth structure and body plan. However, Megalodon differed significantly in scale and proportion. Recent studies suggest a broader head, thicker body, and more robust jaw musculature than earlier reconstructions implied. These refinements reflect ongoing advances in modeling techniques and fossil interpretation. The ecological impact of Megalodon extended beyond direct predation. As a top predator, it influenced the evolution and behavior of prey species. Whale migration patterns, body size increases, and social behaviors may have been shaped in part by pressure from large sharks. The removal of Megalodon from marine ecosystems allowed other predators to expand their roles, contributing to the modern structure of ocean food webs. Megalodon's extinction did not erase its influence. The evolutionary pathways of many marine species were shaped during the time it was present. Its absence created opportunities for new forms of predation, including the rise of social hunting strategies among marine mammals. In this way, Megalodon's legacy persisted long after the species itself disappeared. From a scientific perspective, Megalodon represents an extreme example of how size, specialization, and environmental stability interact. It demonstrates both the advantages and limitations of becoming very large. When conditions align, size confers dominance and efficiency. When conditions change, the same traits can limit adaptability. Today, Megalodon exists only in the geological record and in scientific reconstruction. Its teeth are collected from ancient seabeds, riverbanks, and exposed marine deposits, studied not as symbols of fear or myth, but as data points in a long history of life on Earth. Each fossil adds to a picture that is still incomplete, yet increasingly precise, viewed across deep time. Megalodon was neither anomaly nor inevitability. It was a product of its environment, sustained by abundance, and ended by change. Its life cycle followed the same principles that govern all species: emergence, expansion, stability, and decline. With this understanding, the story of Megalodon settles into the larger narrative of Earth's history, one shaped not by intention or permanence, but by continuous transformation. The ocean moved on, ecosystems reorganized, and time continued without pause. After the disappearance of Megalodon, the oceans did not pause or register loss. Ecological systems adjusted through processes that operate without memory or intention. Predatory pressure shifted, prey populations responded, and energy continued to move through marine food webs in altered pathways. What changed was not the existence of predation, but its form and distribution. In the absence of Megalodon, other large predators expanded their influence. Socially hunting marine mammals increased in ecological importance. Large sharks diversified into niches that required greater flexibility rather than extreme size. Predation became more distributed across multiple species instead of concentrated in a single dominant form. This redistribution reduced dependence on any one predator and increased overall system resilience. Ocean temperatures continued to fluctuate throughout the Pliocene and into the Pleistocene. Ice ages came and went. Sea levels rose and fell repeatedly, coastlines shifted, and shallow marine habitats expanded and contracted in cycles. These changes favored species capable of rapid adaptation, shorter lifespans, and flexible reproductive strategies. Very large, slow reproducing predators became increasingly rare. Modern oceans reflect these long-term processes. No living shark approaches Megalodon in size, not because such size is impossible, but because current conditions do not consistently support it. Prey availability, temperature distribution, and ecosystem structure now favor smaller apex predators operating within more complex food webs. Scientific interest in Megalodon increased as fossil discoveries accumulated during the 19th and 20th centuries. Early interpretations often overestimated size and behavior due to limited comparative data. Over time, improved methods in biomechanics, paleoecology, and climate modeling refined understanding. Each revision reduced uncertainty while reinforcing the central conclusion that Megalodon was real well adapted, and constrained by its environment. Megalodon's story provides insight into how marine ecosystems function over long time scales. It demonstrates that dominance is temporary, dependent on alignment between organism and environment. When that alignment changes, even the most capable species declines. This pattern repeats across the fossil record in both marine and terrestrial systems. The teeth of Megalodon continue to erode slowly from exposed sediments, washed free by waves or rain collected and studied or returned to the sea. Their persistence contrasts with the absence of the animal itself. What remains is evidence, not presence. In geological terms, Megalodon existed briefly. Its entire species duration occupies a small fraction of Earth's history. Yet during that interval, it played a significant role in shaping marine communities. Duration does not determine impact, interaction does. From a deep time perspective, the ocean remains the dominant force. Species emerge, expand, and disappear, while the physical system persists. Water continues to circulate heat, nutrients, and life across the planet. The same processes that supported Megalodon continue to operate, though producing different outcomes. There is no indication that a similar predator will reappear in the near future. Current trends in climate and ocean structure move in directions that reduce the likelihood of supporting such extreme size. Instead, marine ecosystems favor diversity, redundancy, and adaptability. Megalodon's existence is therefore best understood not as a mystery or anomaly, but as a natural result of specific conditions that once prevailed. When those conditions ended, so did the species. Nothing more was required. The ocean continued, currents adjusted, life reorganized. Time remained and remains without reference to what has passed. Long after Megalodon had disappeared from the oceans, humans began to encounter its remains without understanding their origin. Large fossilized teeth were found embedded in rock, riverbeds, and coastal sediments. In many cultures, these objects were interpreted as stones, weapons, or symbols, often called tongue stones, and believed to have fallen from the sky. At that time, there was no framework for understanding deep geological time or extinct marine animals. Scientific interpretation began to change during the 17th century. Naturalists started to recognize similarities between these large fossil teeth and those of living sharks. Gradually, the idea emerged that these objects were not mineral curiosities, but biological remains from animals no longer alive. This shift marked an early step in the development of paleontology. As geology advanced, scientists learned to date rock layers and reconstruct ancient environments. Megalodon teeth were placed within Miocene and early Pliocene sediments, confirming that the species lived millions of years ago rather than alongside humans. The absence of any recent remains became a key line of evidence against survival into modern times. Throughout the 20th century, fossil discoveries increased. Teeth were recovered from dredging operations, construction sites, phosphate mines, and eroded coastal formations. Each new find added information about geographic range, size variation, and population structure. Patterns emerged showing that Megalodon was globally distributed, but not evenly abundant. Modern scientific methods allowed more detailed analysis. Measurements of tooth proportions were compared statistically with those of living sharks. Computer models simulated bite force, swimming efficiency, and energy requirements. Isotopic analysis of fossil material provided insight into water temperatures and habitat preferences. Together, these methods refined understanding without altering the core conclusion that Megalodon was a large, warm, adapted apex predator. Scientific consensus remains that Megalodon is extinct. No physical evidence supports survival into the present. Modern oceans are extensively monitored through fisheries data, underwater imaging, and acoustic tracking. An animal of Megalodon's size would leave clear and unavoidable evidence of its presence. None exists. Public interest in Megalodon continues, often shaped by speculation rather than data. From a scientific perspective, such speculation does not alter interpretation. Paleontology relies on physical evidence, repeatable analysis, and consistency with established ecological principles. When evaluated through this framework, Megalodon fits cleanly within known patterns of evolution and extinction. Research into Megalodon remains active, not because its existence is in question, but because it serves as a valuable case study. It helps scientists understand the limits of body size in marine predators, the relationship between climate and ecology, and the consequences of specialization. Each of these topics remains relevant to the study of both ancient and modern ecosystems. Museums display Megalodon teeth not as symbols of fear, but as records of natural history. They represent an organism shaped entirely by environmental conditions that no longer exist. Their scale invites comparison, but their meaning lies in context rather than spectacle. Through continued study, Megalodon contributes to understanding long-term biological change. It demonstrates that extinction is not an exception, but a common outcome across geological time. Species appear when conditions allow, persist while those conditions remain stable, and disappear when they change beyond tolerance. This process continues today, governed by the same principles that shaped the Miocene oceans. When Megalodon is compared with living marine predators, the differences are not only in size, but in the structure of the oceans themselves. Modern seas operate under conditions that are more variable, more fragmented, and more strongly influenced by polar ice than those of the Miocene. These differences help explain why no direct equivalent to Megalodon exists today. Modern sharks, including the largest species such as the great white shark and the whale shark, occupy ecological roles shaped by present-day constraints. The great white shares similarities with Megalodon in tooth shape, body plan, and hunting strategy, yet it is far smaller and more flexible in diet. It feeds on a wider range of prey sizes and can tolerate cooler waters for extended periods. This flexibility allows survival in environments where prey availability changes seasonally. Whale sharks, by contrast, achieve large size through a completely different strategy. They feed on plankton rather than large animals and rely on filtering enormous volumes of water. Their size does not require high-energy prey, reducing dependence on large marine mammals. This strategy is possible in modern oceans, where plankton blooms remain reliable in certain regions. Megalodon relied on a narrow range of prey types, primarily large marine mammals. This dependence tied its survival directly to whale populations and migration patterns. In the Miocene, these patterns were stable over long periods. In modern oceans, whale populations fluctuate more dramatically due to climate variability and human activity. Complex. Strong temperature gradients separate warm and cold waters. Seasonal changes are more pronounced. These conditions favor predators that can adapt quickly to shifting prey distributions. Large body size, while advantageous in stable systems, becomes costly when conditions change rapidly. Another important difference lies in competition. Modern apex predation is distributed among several species rather than concentrated in one. Killer whales, large sharks, and other predators share overlapping roles. This distribution reduces the likelihood that any single predator will dominate to the extent Megalodon once did. From a physiological perspective, maintaining a very large body in cooler and more variable oceans requires higher metabolic cost. While some modern sharks exhibit partial endothermy, this trait has limits. Sustaining Megalodon scale size would require consistently warm habitats and abundant prey conditions that are now geographically restricted and seasonally unstable. Human influence further alters modern marine ecosystems. Fishing pressure, habitat modification, and climate change have reduced large prey populations and fragmented habitats. Even if environmental conditions once again favored extreme size, current ecological pressures would make long-term persistence difficult. These comparisons reinforce the idea that Megalodon was not simply a larger version of a modern shark. It was a product of a specific oceanic system that no longer exists. Its disappearance reflects environmental change rather than biological inadequacy. Understanding this distinction helps place Megalodon accurately within natural history. It was neither an anomaly nor a mystery. It was an organism precisely matched to its time and limited by that match when conditions changed. As modern oceans continue to evolve, new forms will arise that reflect current constraints and opportunities. They will differ from those of the past, just as Megalodon differed from what came before it. The process remains continuous, shaped by environment, guided by energy flow, and governed by time. Across the full span of Earth's history, very large predators appear only under specific conditions. These conditions include sustained high productivity, stable climate patterns, and reliable access to concentrated energy sources. Megalodon existed during a period when all of these factors aligned. Its size was not an exception to natural rules, but an outcome permitted by them. Biological size is constrained by physics and energy flow. Larger bodies require more food, longer development, and extended reproductive intervals. They also respond more slowly to environmental change. In stable systems, these constraints can be managed. In changing systems, they become liabilities. Megalodon existed near the upper limit of what marine environments could support for an active predatory animal. The fossil record shows repeated examples of large marine predators increasing in size during warm periods. When oceans cool or fragment, maximum body size declines. This pattern is consistent across sharks, marine reptiles, and marine mammals. Megalodon fits this broader trend precisely. Its rise and disappearance align with known shifts in global climate and ocean structure. Energy transfer efficiency also plays a role. Only a small percentage of energy moves from one trophic level to the next. Supporting a predator of megalodon's size required large prey populations sustained by high primary productivity. As productivity patterns changed, less energy reached the top of the food web. Under these conditions, smaller predators with lower energy demands gained advantage. Reproductive strategy further limited adaptability. Megalodon produced few offspring, invested heavily in each, and relied on stable nursery environments. This strategy worked when coastal systems were extensive and predictable. As coastlines shifted and shallow seas declined, recruitment became less reliable. Population recovery slowed. Over time, these pressures accumulated. Decline did not occur everywhere at once. Some populations persisted longer than others, but genetic exchange between regions likely decreased as habitats fragmented. Reduced connectivity further weakened resilience. Eventually, the species crossed a threshold beyond which recovery was not possible. At that point, extinction followed without sudden catastrophe. This outcome is common in the fossil record and reflects long-term imbalance rather than sudden failure. From a scientific perspective, Megalodon provides a clear example of how apex predators function within large ecosystems. Its life cycle illustrates the relationship between environment, anatomy, behavior, and survival. Each stage depended on the conditions that preceded it. Modern marine ecosystems continue to change. While no direct equivalent to Megalodon exists today, the principles that governed its life remain active. Predator size, distribution, and behavior continue to respond to temperature, productivity, and prey structure. These responses occur gradually, often unnoticed until changes accumulate. The study of Megalodon does not suggest return or repetition. Instead, it clarifies limits. It shows what oceans can support under specific conditions, and what happens when those conditions no longer apply. The species existed, persisted, and ended within the same natural framework that governs all life. The ocean continued to circulate, ecosystems reorganized, and biological processes moved forward. Nothing paused, nothing remembered, and nothing needed to. When the full life cycle of Megalodon is viewed without emphasis or narrative framing, it appears as a sequence of biological processes governed by environment, energy availability, and time. There is no distinct beginning in a meaningful sense, only gradual emergence from ancestral forms that were already successful predators in their own right. Reproduction initiated each life cycle in warm, shallow marine environments. Embryonic development occurred internally, protected from external conditions. Birth produced relatively few offspring, each already large enough to function independently. This initial size reduced early mortality but increased dependence on stable nursery habitats. Juvenile megalodons occupied coastal waters for extended periods. Growth during this phase was continuous and supported by frequent feeding. Teeth replaced rapidly as prey capture occurred. Sensory systems developed in parallel with body size, improving detection of movement and chemical cues. Survival during this stage depended largely on habitat stability and food availability rather than direct competition. As body size increased, habitat use expanded. Subadult individuals transitioned into deeper and more open waters. Diet shifted toward larger prey. Feeding frequency decreased as individual meals provided greater energy return. Growth slowed but did not stop. Physiological efficiency improved as swimming mechanics stabilized. Adulthood represented a period of relative equilibrium. Body size reached a functional maximum. Energy intake balanced maintenance and reproduction. Individuals moved widely but predictably, following temperature gradients and prey distribution. Reproductive cycles repeated at long intervals. Mortality risk remained low. Aging occurred gradually. There is no evidence of abrupt senescence. Declines in efficiency likely manifested as reduced hunting success rather than sudden failure. Older individuals may have relied more on scavenging or smaller prey. Eventually, death occurred through injury, starvation, or environmental stress. The body returned to the ecosystem through decomposition and scavenging. At the population level, these individual life cycles overlapped to create continuity. As long as environmental conditions supported reproduction and juvenile survival, population stability persisted. When those conditions weakened, recruitment declined. Adult mortality then exceeded replacement. Extinction followed as a population-level outcome, not an individual event. No single generation experienced the end of the species. Instead, fewer young reached maturity. Geographic range contracted. Genetic diversity decreased. Eventually, no reproducing individuals remained. From this perspective, Megalodon's life cycle did not end differently from that of any other species. It followed the same constraints that apply universally. Its size did not exempt it from dependence on environmental balance. What distinguishes Megalodon is scale rather than mechanism. The processes involved, growth, feeding, reproduction, aging, and extinction, are identical in structure to those of smaller organisms. Only the quantities differ. This understanding removes the need for speculation or exaggeration. Megalodon was not an anomaly. It was a predictable outcome of favorable conditions and a predictable casualty of their loss. The ocean did not change in response to Megalodon's extinction. It continued to operate according to physical and chemical laws. New species filled available niches. Energy continued to flow. From the standpoint of deep time, the presence of Megalodon was brief, and its absence unremarkable. The system remained. Understanding Megalodon requires attention to time scales far beyond direct observation. The species existed for several million years, a duration that exceeds the entire span of human civilization by orders of magnitude. Events that appear slow or insignificant on a human scale accumulate meaningfully over geological time. Small changes in temperature, sea level, or prey distribution become decisive when sustained across thousands of generations. Geological dating methods provide the framework for placing Megalodon accurately in time. Stratigraphy allows scientists to identify the relative age of sediment layers in which fossil teeth are found. Radiometric dating of associated volcanic material refines these estimates. Together, these methods consistently place Megalodon within Miocene and early Pliocene deposits, with no verified presence in younger layers. Certainty in extinction does not rely on a single absence, but on patterns. The fossil record shows a gradual reduction in Megalodon remains toward the late Pliocene, followed by complete disappearance. In contrast, other shark species continue to appear in younger sediments. This selective absence supports extinction rather than preservation bias. Scientific models also test feasibility. Population viability analyses consider reproduction rate, lifespan, and prey requirements. When applied to modern oceans, these models show that a Megalodon-sized predator could not persist unnoticed. Energy demands would require frequent interaction with large prey, leaving clear ecological and physical evidence. None is present. Ocean monitoring further supports this conclusion. Modern seas are surveyed through fishing data, satellite tracking, acoustic sensors, and deep-sea exploration. Large marine animals leave detectable signatures in these systems. Even elusive species such as deep-diving whales are regularly recorded. An organism of Megalodon's size would not escape detection. Measurement of fossil teeth provides additional consistency. Tooth size distribution follows predictable patterns over time. Earlier specimens show gradual increase in average size, while later specimens stabilize before declining. This pattern aligns with ecological expansion followed by constraint. It does not support sudden disappearance or hidden survival. Uncertainty remains in details rather than fundamentals. Exact maximum size, precise growth rate, and specific migration routes continue to be refined. These uncertainties are typical in paleontology and do not undermine core conclusions. They reflect the limits of available data rather than gaps in understanding. Scientific knowledge advances through accumulation rather than revelation. Each new fossil adds resolution. Each new method refines interpretation. Over time, independent lines of evidence converge. In the case of Megalodon, they converge consistently toward the same outcome. This convergence allows confidence without speculation. Megalodon existed, functioned as a large marine predator, and became extinct as environmental conditions changed. No additional explanation is required. From a scientific standpoint, this is sufficient. The ocean continued to change. Life continued to adapt, and evidence accumulated quietly in sediment. Over long spans of time, systems persist even as individual components change. This principle applies to oceans, climates, and biological communities alike. Megalodon existed within such a system, responding to conditions rather than directing them. And when those conditions shifted beyond tolerance, the species declined without disruption to the larger process. Sediment continued to accumulate on the seafloor layer by layer, preserving chemical signatures, skeletal fragments, and teeth shed during ordinary life. These deposits recorded presence and absence without emphasis. No marker exists to indicate significance or loss. Only change in composition over time. Ocean circulation adjusted gradually. Currents strengthened or weakened. Upwelling zones shifted location. Productivity increased in some regions and declined in others. These changes influenced the distribution of plankton, then fish, then marine mammals. Predators responded in turn, moving, adapting, or disappearing as constraints narrowed. The absence of Megalodon did not create a void. Other predators occupied available roles, not by replacement, but by redistribution of energy flow. Predation pressure remained, but spread across multiple species with different strategies and sizes. This distribution increased system flexibility. In modern oceans, this flexibility is evident. No single predator dominates across all regions. Instead, apex predation is shared, allowing ecosystems to respond to variability more effectively. This arrangement reflects long-term selection for resilience over extremity. Megalodon's size, while effective under stable conditions, represented specialization at the edge of feasibility. Such specialization does not persist when environments become variable. The fossil record repeatedly demonstrates this outcome across many lineages. Time continued without reference to species identity. Processes that supported Megalodon once continue to operate, producing different results under new constraints. Warm intervals give rise to larger forms. Cooling favors smaller, faster reproducing organisms. Human study introduces perspective but not influence. Interpretation occurs long after events conclude. Fossils do not respond to observation. They remain in place until uncovered, unaffected by meaning assigned to them. Understanding emerges slowly, through accumulation of data, through repeated comparison, through elimination of alternatives. In this process, speculation fades while structure remains. The life cycle of Megalodon, from emergence to extinction, fits within this structure. It does not require exception or embellishment. It requires only recognition of scale, duration, and constraint. Across deep time, oceans remain in motion, systems adjust, and life continues within limits defined by physics and energy. The sequence does not end, it proceeds. Across geological time, permanence does not exist as a condition, only duration. Megalodon persisted for millions of years. Yet even that span represents a brief interval when measured against the age of the oceans themselves. This perspective is central to understanding extinction as a routine outcome rather than an exceptional event. Marine environments are shaped primarily by physical forces, temperature gradients, plate tectonics, atmospheric circulation, and the chemistry of seawater. Biological communities respond to these forces rather than control them. When the physical framework changes, biological structure follows. During the Miocene, tectonic movement altered seaways and ocean basins. Gradual closure of ocean passages changed circulation patterns. These shifts influenced nutrient distribution and productivity. Regions that once supported dense prey populations became less reliable over time. As productivity patterns shifted, food webs reorganized. Large prey species adapted by changing distribution or behavior. Some became faster. Others migrated longer distances, and some declined entirely. Predators dependent on a narrow range of prey experienced increasing constraint. Megalodon's absence from younger sediments reflects this process. Its extinction did not require catastrophe. It required only sustained mismatch between biological demand and environmental supply. Over enough generations, this mismatch produced decline. The fossil record preserves this outcome without commentary. Layers above the last megalodon teeth show continued marine life. Sharks of smaller size, whales with altered forms, and ecosystems functioning under new parameters. There is continuity without repetition. From a biological standpoint, specialization always carries risk. The more tightly a species is matched to specific conditions, the less flexible it becomes. Megalodon represented extreme efficiency under particular circumstances. When those circumstances shifted, efficiency became limitation. Modern marine systems demonstrate the same principle. Species that tolerate wide temperature ranges, varied diets, and flexible reproductive strategies persist more readily through change. Those with narrow requirements decline. Megalodon size constrained reproduction speed, population density, and dispersal flexibility. These constraints were not weaknesses until environmental variability increased. Once variability rose beyond tolerance, extinction followed as an outcome of process. The absence of Megalodon today does not imply failure or inferiority. It reflects alignment with a past environment rather than the present one. Many species now dominant will eventually face similar outcomes under future conditions. From the perspective of Earth systems, extinction is neither loss nor gain. It is transition. Matter remains, energy flows continue, and structure reorganizes. The ocean does not retain memory. Sediment records sequence, not significance. Time proceeds and systems adapt within limits. When Megalodon is removed from consideration as an individual organism and viewed only as a component of a larger system, its disappearance becomes one instance within a continuous pattern. Oceans have always supported dominant predators, and they have always replaced them as conditions changed. No role remains vacant for long, only redistributed. Marine ecosystems operate through energy transfer rather than hierarchy. Primary production at the surface supports successive levels of consumption. When energy availability decreases at any level, the effect propagates upward. Large predators are affected first because their energy requirements are greatest. During the late Miocene and early Pliocene, changes in productivity altered this balance. Even modest reductions in prey density would have had significant effects on Megalodon populations. Fewer successful hunts meant longer intervals between feeding. Over time, this reduced reproductive output and juvenile survival. The system did not collapse. Instead, energy flow adjusted. Smaller predators increased in relative abundance. Marine mammals altered behavior and distribution. Predation pressure remained, but it was expressed through multiple species rather than one dominant form. This redistribution increased adaptability at the system level. When conditions fluctuate, systems with many moderate-sized predators respond more effectively than systems dominated by a single extreme specialist. This pattern is repeated across ecological history. The continued presence of sharks in modern oceans reflects this outcome. Sharks remain successful not because of size, but because of diversity. They occupy many niches, exploit many food sources, and reproduce under a wide range of conditions. Megalodon represented one endpoint of specialization. Its existence demonstrates the maximum extent of a strategy rather than a norm. Such endpoints are informative because they define limits. In the fossil record, these limits appear repeatedly. Large forms emerge during stable warm periods, then disappear as variability increases. Smaller, more adaptable forms persist. Understanding this pattern does not require narrative interpretation. It follows directly from ecological principles. Energy constraints, reproduction rates, and environmental variability interact predictably over long timescales. Megalodon's life cycle fits entirely within this framework. From emergence to extinction, each phase reflects response rather than agency. The species did not change the ocean shaped the species. This relationship remains unchanged. Modern ecosystems continue to follow the same rules. Only the participants differ. Sediment continues to accumulate. Water continues to circulate. Life continues to reorganize. The sequence extends forward without pause, without reference. When examined at sufficient scale, individual species become brief expressions of broader physical and biological processes. Megalodon existed long enough to leave a measurable imprint in the fossil record, yet not long enough to alter the underlying structure of the ocean. This distinction is important for understanding its place in natural history. Duration alone does not indicate permanence. Many species persist for millions of years and then disappear without leaving descendants. Others exist for shorter spans, yet give rise to long-lasting lineages. These outcomes depend on compatibility with changing conditions rather than length of existence. Megalodon's compatibility was high during the Miocene. Ocean temperatures remained elevated. Prey density supported large body size. Nursery habitats existed along extensive coastlines. Under these conditions, the species functioned efficiently. As those conditions changed, compatibility declined. The decline was gradual and spatially uneven. Some regions remained suitable longer than others. This produced staggered disappearance rather than sudden extinction. Such patterns are common among widely distributed marine species. Observation of these patterns relies on preserved evidence. Fossils represent only a fraction of past life. Even so, consistent absence across multiple regions and sediment layers provides strong indication of extinction. Megalodon's absence from younger deposits is systematic rather than random. Modern technology has expanded observation capacity. Satellite imaging, acoustic monitoring, genetic sampling, and global fisheries data provide extensive coverage of ocean life. These tools detect organisms far smaller and rarer than Megalodon would be. Their failure to detect such a species reinforces conclusions drawn from fossils. Limits of observation still exist. Deep-sea environments remain difficult to survey completely. However, the size and ecological impact of Megalodon would require interaction with surface systems. Such interaction would produce unavoidable evidence. Scientific certainty is built through convergence. Independent lines of evidence align. Fossil chronology, ecological modeling, physiological constraints, and modern observation all indicate the same outcome. Megalodon existed and is no longer present. This certainty does not diminish interest. Instead, it allows focus to shift from speculation to understanding. The species becomes a reference point for studying ecological limits rather than an object of mystery. Across deep time, reference points accumulate. Each extinct species adds resolution to understanding how life responds to change. Megalodon contributes by illustrating the upper boundary of predatory size under natural conditions. The boundary remains. Conditions that once permitted such size no longer persist globally. Should conditions shift again, different outcomes may arise, but they will reflect new constraints rather than repetition. The ocean continues to function within physical limits. Energy moves upward from primary production. Predators respond to availability. Time advances without regard to individual forms. Across geological history, patterns repeat without exact duplication. Warm periods expand marine productivity, cold periods restrict it. Sea levels rise, then fall. Coastlines advance, then retreat. Within these cycles, species appear that fit prevailing conditions and disappear when those conditions no longer apply. Megalodon existed during one such interval of relative stability. For millions of years, environmental change occurred slowly enough that biological systems could adjust without collapse. Under these circumstances, large body size remained viable. Energy input exceeded demand. Reproductive success remained sufficient to sustain populations. This balance did not require constancy. Short-term fluctuations occurred: storms, regional cooling, changes in prey abundance. These events were absorbed by the system without long-term disruption. Stability emerged from duration rather than uniformity. As cycles progressed, the rate and magnitude of change increased. Cooling accelerated. Ocean circulation reorganized. Productivity patterns shifted more rapidly. Under faster change, buffering capacity declined. Systems became more sensitive to disturbance. Large specialists were affected first. Smaller, more flexible organisms adjusted more readily. This sequence is observed repeatedly in the fossil record. Megalodon followed the same pattern. The repetition of this outcome does not diminish its significance. Instead, it clarifies mechanism. Extinction is not an isolated event. It is a phase within long cycles of expansion and contraction. These cycles continue today. Modern oceans are undergoing rapid change. Species distributions shift in response to temperature and chemistry. Some populations decline, others expand. The same principles operate, though participants differ. Understanding Megalodon within this context removes emphasis from individual traits and places focus on system dynamics. The species becomes an indicator of conditions rather than an exception to rules. From this perspective, the presence of Megalodon marks a peak in marine predator size during a specific climatic regime. Its absence marks transition to a different regime. Neither state is permanent. Sediment layers preserve this alternation. One layer records presence, another absence, another presence of different forms. Over time, these layers accumulate into a continuous record of change. The record does not end. It extends forward beyond present observation. Future layers will document current ecosystems, their changes, and their outcomes. The ocean remains the setting. Physical laws remain constant. Biological responses vary. Cycles continue. Without reference to individual species in scientific study, absence is not empty. When a species no longer appears in the fossil record, when expected evidence fails to appear despite extensive sampling, that absence becomes data. In the case of Megalodon, absence is consistent, widespread, and persistent beyond a certain point in geological time. Sedimentary layers younger than the early Pliocene contain abundant marine fossils. Sharks are present. Whales are present. Fish are present. Yet Megalodon teeth are not. This selective absence indicates a biological change rather than a failure of preservation. The conditions that once recorded Megalodon continued to record other organisms. Absence also appears in ecological modeling. When the energy requirements of a Megalodon-sized predator are applied to modern ocean conditions, models show instability. Prey density would not support sustained populations. Reproductive output would fail to offset mortality. These outcomes align with fossil evidence. Absence further appears in modern observation. Contemporary oceans are among the most monitored environments on Earth. Large marine animals are detected through direct sighting, acoustic signals, feeding traces, and population surveys. No evidence consistent with Megalodon exists. This absence is meaningful because detection probability would be high. Together, these absences converge. They reinforce one another. They define a boundary between past and present ecosystems. From this boundary, interpretation shifts from speculation to context. Megalodon becomes a reference for understanding what oceans once supported, not something that might still exist. Its significance lies in what it reveals about environmental capacity. Absence also emphasizes continuity. The ocean did not become empty after Megalodon disappeared. Instead, new patterns emerged. Predation continued. Energy flowed. The system reorganized without disruption to underlying processes. This reorganization highlights adaptability at the system level. While individual species may be constrained, ecosystems as wholes adjust. Roles are redistributed rather than erased. Understanding this helps avoid misinterpretation. Extinction does not imply collapse. It implies transition. The life cycle of Megalodon ended, but the process that produced it did not. Sediment continued to form. Water continued to move. Life continued to respond. Absence remained recorded as clearly as presence once was. Viewed across sufficient time, the ocean functions as a continuous system rather than a sequence of events. Temperature shifts, circulation changes, biological turnover all occur within a framework that does not reset or conclude. Megalodon existed within this system for a defined interval and then ceased to exist, while the system itself continued without interruption. Water chemistry adjusted gradually as atmospheric conditions evolved. Levels of dissolved oxygen, carbon dioxide, and nutrients changed in response to climate and tectonic movement. These changes influenced which organisms could thrive. Large predators such as Megalodon were sensitive to these parameters because of their high metabolic demands. Ocean basins themselves changed shape. Continental drift altered coastlines and seaways. Some passages narrowed and others closed entirely. These physical changes modified current strength and direction. Regions that once received steady nutrient input experienced decline. Others became newly productive. Biological communities followed these shifts. The life cycle of Megalodon intersected with this physical evolution. Its expansion occurred when circulation supported widespread productivity. Its decline followed when circulation patterns became more segmented. The relationship between physical structure and biological outcome remained direct. No evidence suggests that Megalodon adapted behaviorally at a rate sufficient to overcome these changes. Large body size limited flexibility. Reproductive cycles were long. Population recovery was slow. Under increasing variability, these traits reduced persistence. Other species responded differently. Smaller sharks diversified. Marine mammals developed new strategies. Ecosystems reorganized toward configurations better suited to emerging conditions. This process is ongoing. Modern oceans continue to respond to physical forcing. Species distributions shift. Food webs reorganize. The principles observed in the Miocene apply equally today. From this perspective, Megalodon represents a data point within a continuous record. Its life cycle provides information about thresholds, limits, and responses. It does not require emphasis beyond its role in illustrating these principles. The ocean retains no memory of individual species. It reflects only current conditions. When conditions change, outcomes change. Sediment layers accumulate silently. Water circulates continuously. Life reorganizes incrementally. The system remains active, unbroken, and ongoing. In any ecological system, thresholds exist beyond which adjustment becomes unlikely. These thresholds are not fixed points, but ranges where small changes accumulate until reversal is no longer possible. For Megalodon, multiple thresholds were approached simultaneously during the late Miocene and early Pliocene. Thermal tolerance formed one such boundary. As global temperatures declined, warm water habitats contracted. Megalodon could tolerate moderate cooling, but only within limits. Sustained exposure to colder waters increased metabolic cost and reduced efficiency. Once suitable thermal zones became fragmented, movement between them required greater energy expenditure. Prey availability represented another threshold. Large marine mammals remained present, but their density decreased in many regions. Even small reductions in prey frequency had amplified effects on a predator with high energetic demand. Missed feeding opportunities could not be easily compensated. Habitat structure also imposed limits. The reduction of shallow coastal areas constrained nursery habitat availability. Juvenile survival depended on these environments. When they became less extensive and more unstable, recruitment declined. Population structure became increasingly weighted toward older individuals. These constraints interacted. Reduced recruitment increased reliance on existing adults. Increased energetic stress reduced adult longevity. Together, these pressures narrowed the margin for persistence. Importantly, none of these thresholds required extreme change. Gradual shifts were sufficient when sustained over long durations. This characteristic is common in extinction processes observed in the fossil record. Once thresholds were crossed, recovery became improbable. Even if conditions briefly improved, population size and genetic diversity may have fallen too low to respond effectively. Extinction followed as a delayed outcome. Such processes continue to operate in modern ecosystems. Thresholds are crossed quietly. Effects emerge later. Interpretation often occurs only in retrospect. Megalodon's extinction reflects this pattern. It was not sudden, not localized, and not catastrophic. It was the result of sustained constraint acting on a highly specialized organism. Understanding this reinforces a broader principle. Biological success depends not on dominance, but on compatibility with change. When compatibility declines, persistence becomes unlikely regardless of size or strength. The ocean continued to operate within physical laws. Life responded within biological limits. Outcomes followed naturally. The record preserves this sequence without emphasis, without exception. When the life cycle of Megalodon is reviewed again, not as a sequence of events, but as a functioning biological system, its dependence on environmental stability becomes increasingly clear. Each stage of life operated effectively only because surrounding conditions remained within a narrow and predictable range. Reproduction depended on warm, shallow waters that persisted over long periods. These environments were not temporary shelters. They were stable features of the Miocene coastline. Their persistence allowed repeated use across generations. Without reliable nursery zones, internal gestation alone would not have ensured juvenile survival. Early growth required frequent access to manageable prey. Juvenile megalodons fed often, their smaller size demanding steady intake of energy. Shallow coastal ecosystems provided fish, rays, and smaller sharks in sufficient density. This density reduced the need for long-distance movement during early life, conserving energy and lowering risk. As individuals matured, their increasing size reduced vulnerability but increased energetic demand. At this stage, the transition into deeper and more open waters became necessary. This transition succeeded only because prey availability expanded with body size. Larger prey compensated for lower feeding frequency. Adulthood functioned as a period of energetic balance. Energy intake from infrequent large meals offset the cost of maintaining a large body. Reproductive investment occurred intermittently rather than continuously. This balance depended on predictable prey migration and relatively stable water temperatures. Throughout this cycle, mortality remained low when conditions were favorable. Juvenile mortality decreased in protected habitats. Adult mortality remained limited due to size and lack of predators. Population structure remained balanced as long as recruitment replaced natural loss. Aging introduced gradual inefficiencies, but did not immediately disrupt survival. Older individuals remained capable of feeding. Tooth replacement mitigated wear. Decline occurred slowly rather than abruptly. This entire cycle relied on continuity. No stage was independent. Disruption at any point propagated forward. Reduced nursery stability affected juvenile survival. Reduced juvenile survival affected adult population size. Reduced adult numbers lowered reproductive output. Environmental change acted first on the most sensitive stages. Juvenile habitats declined. Recruitment weakened. Population age structure shifted. These changes unfolded over thousands of years, beyond the perception of any individual organism. Viewed this way, extinction appears not as a final event, but as the cumulative result of life cycle imbalance. Megalodon did not fail at adulthood, it failed at renewal. This pattern is consistent across many extinct species. Life cycles that require multiple stable conditions are less resilient to gradual change. Flexibility at one stage cannot compensate for rigidity at another. The fossil record preserves this outcome indirectly. Large adult teeth remain common until late stages. Smaller juvenile teeth decline earlier. This shift suggests declining recruitment before complete disappearance. Understanding extinction through life cycle dynamics emphasizes process over outcome. It removes focus from the end and places it on the gradual loss of balance. The ocean continued to change, life cycles adjusted or ended, and new systems formed. After Megalodon disappeared from the oceans, the marine environment did not enter a period of disruption or instability. Instead, existing processes continued and adjusted gradually. The absence of a single apex predator altered patterns of energy flow, but did not interrupt them. Marine mammal populations responded first. In regions where Megalodon had once exerted strong predatory pressure, some whale species expanded their ranges or altered migration timing. Grouping behavior became more common in certain lineages. These changes were not sudden adaptations, but gradual shifts favored over many generations. Other predators filled portions of the ecological space left behind. Large sharks continue to function as important hunters, though at smaller sizes. Early forms of social predation among toothed whales increased in effectiveness. These predators relied on cooperation rather than size alone, allowing them to hunt a broader range of prey under more variable conditions. Food webs became more distributed. Instead of energy passing through a small number of extremely large predators, it moved through multiple intermediate-sized predators. This distribution reduced reliance on any single species and increased resilience to environmental fluctuation. Ocean productivity continued to vary with climate. Cooling trends persisted through the Pliocene and into the Pleistocene. Ice ages intensified temperature gradients and strengthened seasonal variability. These conditions favored mobility, behavioral flexibility, and shorter life cycles. Shallow coastal environments continued to change as sea levels fluctuated. Some nursery habitats disappeared permanently. Others reformed temporarily during interglacial periods. Species capable of exploiting these transient habitats gained advantage. Those requiring long-term stability declined. The absence of Megalodon did not remove predation from marine systems. Instead, it altered scale. Predation pressure became more frequent but less concentrated. This shift influenced prey evolution differently, favoring speed, coordination, and rapid reproduction rather than structural reinforcement alone. Over time, modern marine ecosystems emerged. Large baleen whales persisted. Toothed whales diversified. Sharks occupied many niches rather than one dominant form. The system reflected adaptation to variability rather than stability. From a geological perspective, this transition represents continuity rather than replacement. The ocean remained the same physical system, responding to the same forces. Biological structure changed to match new constraints. Megalodon's absence became normalized. Later ecosystems developed without reference to its existence. No trace of behavioral memory persisted. Only fossil evidence recorded the difference. The ocean continued to circulate, species adjusted, and balance reformed under new conditions. When the full span of Megalodon's existence is placed against the background of Earth's history, its life becomes a measure of environmental possibility rather than exception. The species appeared when conditions aligned, persisted while those conditions remained stable, and disappeared when alignment was lost. No further explanation is required. Across millions of years, the ocean provided warmth, space, and sufficient energy to support extreme size. During that interval, Megalodon functioned efficiently within its ecological role. Its anatomy, behavior, and life cycle matched the demands and opportunities of the Miocene seas. This compatibility sustained the species without the need for constant adaptation. As conditions shifted, the same traits that once supported success limited flexibility. Large body size required reliable prey. Slow reproduction required stable nursery habitats. Long lifespan required environmental consistency. When these requirements could no longer be met simultaneously, population renewal declined. The end of Megalodon did not mark a failure of design. It marked the end of suitability. Environmental systems changed direction. Biological systems followed. From the perspective of deep time, this sequence repeats continuously. Species emerge in response to opportunity. They persist within constraint. They disappear when constraint outweighs opportunity. The ocean records these transitions without emphasis through sediment, chemistry, and fossil remains. Today, the ocean continues to operate within the same physical framework. Temperature gradients shift, currents circulate, nutrients move upward through food webs, predators and prey adjust in response. The identities of dominant species change, but the process remains constant. Megalodon's teeth remain as physical evidence of this process. They do not represent threat or mystery. They represent alignment between organism and environment at a particular moment in Earth's history. Their presence in stone marks a time when such alignment was possible. There is no indication that this alignment will return in the same form. Modern oceans differ in structure, temperature, and variability. Future oceans will differ again. New forms will arise that reflect future constraints, not past ones. In this way, Megalodon belongs fully to its time. It does not extend into the present, and it does not need to. Its role has already been fulfilled within the larger sequence of natural history. The ocean continues. Energy flows. Life reorganizes. Time does not pause and does not repeat exactly. What remains is process and continuity moving forward without reference. Even after a sequence appears complete, the underlying system does not end. The story of Megalodon does not require a final boundary, because it is embedded within processes that continue beyond any single species. What follows is not an extension of the animal's life, but an extension of context. Marine sediments that no longer contain Megalodon teeth continue to accumulate. Grain size changes with current speed. Chemical composition reflects temperature and productivity. Microfossils record plankton communities that replaced earlier ones. These records show continuity rather than absence. Life did not diminish when Megalodon disappeared. It reorganized. Predatory pressure remained an essential component of marine ecosystems. Energy continued to move upward through food webs. The scale of predation shifted downward, distributed among many species rather than concentrated in one. This redistribution altered evolutionary pressures across multiple lineages. Whale populations responded over long timescales. Some lineages increased in number, others declined. Body size trends shifted. Migration routes adjusted in response to climate cycles rather than predation alone. These changes occurred gradually, measurable only through fossil comparison across layers separated by thousands of years. Sharks continued to persist as a group. Their success was not dependent on extreme size. Instead, diversity allowed occupation of many niches. Some specialized in speed, others in depth, others in feeding strategy. This diversity increased resilience under variable conditions. The principles illustrated by Megalodon's life cycle apply broadly. When environmental stability supports specialization, specialized forms expand. When variability increases, generalist strategies prevail. This balance shifts repeatedly through time. From a geological standpoint, the Miocene represents one configuration among many. Earlier periods supported different dominant predators. Later periods supported others. None persisted indefinitely. Each reflects a temporary alignment of physical and biological factors. Modern oceans represent the current state of this ongoing sequence. They are neither diminished nor incomplete compared to the past. They are different, shaped by different constraints. Future oceans will differ again. The absence of Megalodon does not represent loss in a functional sense. It represents transition. The same energy that once supported it now supports other forms. Sediment continues to fall. Currents continue to move. Life continues to respond. There is no endpoint within the system itself. When time is viewed at planetary scale, distinctions between past, present, and future become less defined. Processes repeat with variation. Patterns recur without duplication. Megalodon occupies one position within this continuum. The emergence of large marine predators has occurred multiple times in Earth's history. Marine reptiles dominated earlier oceans. Large sharks followed. Marine mammals later assumed some apex roles. Each transition reflects environmental context rather than linear progression. No trend leads inevitably toward larger or smaller forms. Instead, size fluctuates within constraints imposed by temperature, productivity, and habitat structure. Megalodon represents a peak under one set of constraints, not a goal or culmination. The fossil record does not privilege survival. It records outcomes. Many species that were highly successful within their context left no descendants. Others that appeared insignificant persisted. These outcomes are shaped by compatibility rather than dominance. Human interpretation adds narrative, but natural systems operate without it. Extinction does not require meaning. Persistence does not imply success. Both are responses to conditions. Understanding this removes urgency from disappearance. It places emphasis on continuity of process. The ocean does not move toward improvement or decline. It moves toward balance under current conditions. As conditions change, a balance shifts. Species respond or disappear. New forms arise. The cycle repeats. Megalodon's presence and absence are equally ordinary within this framework. Time continues, systems adjust, and history accumulates without pause. This final extension does not introduce new information. It slows the perspective further, reinforcing continuity rather than conclusion. The ocean remains governed by physical laws. Density gradients drive circulation. Temperature influences metabolism. Energy limits size. These principles apply equally across eras. Life responds within these limits. When energy is abundant and predictable, large forms emerge. When energy becomes variable, smaller and more flexible forms persist. Megalodon followed this pattern precisely. Its life cycle reflected opportunity. Its extinction reflected constraint. Neither outcome required exception. In listening slowly, repetition reinforces understanding. The same principles appear again and again across different contexts. This repetition mirrors natural processes themselves. Nothing in Earth's history concludes absolutely. Each phase transitions into the next. Records overlap. Boundaries blur. The story of Megalodon blends into the larger record of the ocean. It does not stand apart. Water continues to circulate. Sediment continues to settle. Life continues to adapt. There is no final moment, only continuation. At the scale of millions of years, continuation is the default state. What appears complete at one level becomes a transition at another. After Megalodon, after the Miocene, after the Pliocene, the ocean continued to operate through the same governing principles that existed long before any single species emerged. Water temperature continued to fluctuate as orbital cycles altered solar input. Glacial periods expanded and retreated. Sea levels rose and fell repeatedly, reshaping coastlines and continental shelves. Each change altered habitat availability without altering the fundamental nature of the ocean itself. Marine life responded incrementally. Species distributions shifted toward equatorial regions during colder phases and expanded poleward during warmer intervals. Productivity concentrated in regions where currents and nutrient upwelling aligned. Predators followed prey. Prey followed resources. The system adjusted continuously. Sharks remained present throughout these changes. Their persistence reflected structural efficiency rather than dominance. Smaller body sizes reduced energetic demand. Faster reproductive cycles increased adaptability. Broad diet ranges reduced dependence on any single prey group. These traits proved compatible with variability. Marine mammals continue to evolve under different pressures. Social behavior increased in importance. Communication and coordination allowed efficient hunting without reliance on extreme size. These developments reflected environmental constraints rather than competitive replacement. The absence of Megalodon did not alter the rules governing predator-prey interaction. It altered only scale. The same interactions occurred at different magnitudes. Energy still moved upward through trophic levels. Mortality still shaped population structure. Selection still favored compatibility. Sediment layers accumulated above those that once contained Megalodon remains. Each layer preserved chemical and biological information reflecting prevailing conditions. Together, these layers form a continuous archive rather than a segmented record. Human presence represents a very recent addition to this archive. Human influence has altered marine systems rapidly, but it operates within the same physical constraints. Energy availability, temperature tolerance, and reproductive capacity remain decisive factors. From a deep time perspective, current changes are part of the same continuum. They differ in rate, not in principle. Future ecosystems will reflect present constraints just as Miocene ecosystems reflected theirs. The life cycle of Megalodon remains informative because it illustrates these principles clearly. Its emergence, persistence, and disappearance align closely with environmental context. Nothing more is required to understand it. Beyond any specific epoch, the ocean operates through repetition rather than progression. Physical forces interact continuously, producing outcomes that differ in detail but not in structure. Megalodon existed within one expression of this structure. Its absence reflects a different expression rather than an interruption. Ocean circulation continues to redistribute heat and nutrients. Surface waters absorb energy from sunlight. Deeper waters store and release heat slowly. These movements regulate biological productivity across regions and seasons. When circulation patterns shift, biological communities adjust accordingly. Primary production remains the foundation of marine systems. Plankton growth determines the amount of energy available to higher trophic levels. Variations in light, nutrient input, and temperature influence this growth. Changes at this base propagate upward, affecting fish, marine mammals, and predators. Large predators respond to these changes indirectly. They do not track plankton directly. They track prey that depend on plankton. When prey distributions shift, predators either follow, adapt, or decline. Megalodon followed when conditions allowed. It declined when following became inefficient. The continuity of sharks through these changes demonstrates structural resilience. Sharks occupy multiple ecological roles. They persist by adjusting size, behavior, and diet rather than maintaining dominance through scale alone. This adaptability explains their long-term survival as a group. Marine mammals demonstrate a parallel pattern. Lineages expand and contract. Some increase in size during favorable periods. Others emphasize social strategies. These responses reflect the same environmental constraints that shaped Megalodon. The fossil record records these adjustments without distinction. Layers accumulate containing different assemblages of species. No layer represents permanence. Each reflects a temporary balance. Interpretation assigns meaning only after the fact. Natural systems operate without such framing. They respond to immediate conditions rather than historical precedent. The absence of Megalodon does not alter the ongoing function of the ocean. It represents one outcome among many possible outcomes produced by changing constraints.